All right, well, what we're going to do is we're going to talk about how to solve a problem that's a little bit different than what you would use in order to find using the washer or um, the disk method. And so what we have right here is we're going to take this solid, all right, or this region, and we have this graph right here. So if you graph this, you realize that, okay, I'm going to factor that out a little bit. I have x, and then I'll have 1 minus x. And I have this function, all right, which we see is going to start here at 0 and goes to 1, all right, and it's a parabola, and it's going to be bounded by the x-axis. And what we're going to do is we're going to revolve this solid around the x or the y-axis. Woo, woo, woo. Now, when we've done this in the past, we took regions like this and we said, okay, well, there's a gap here, so that we require like 2 different circles, all right, because our cross sections would be circles. However, something weird happens when we try to do it that way. Because what you realize is that you have one big R and the small little r happen to be the same thing, or at least the same function. That's a no-no. So the question is, why or how can we find these values, all right, using what we know about revolutions? Well, the problem is that we can't use what we know about washer and disk. What we're going to do is we're going to do something else, which is called the shell method, all right, the shell method. And what is the shell method? Well, the shell method, essentially what we're doing is we're taking and we're creating shells. So that's what we're going to do. We're going to take a little shell, and we're going to draw this value right here. And this value is going to be, all right, some sort of x units away. And we'll just say x sub 0 right there. And so it's x units away. And what we're going to do is we're going to take this value, we're going to rotate it around this y-axis like this. Now, when we do that, what happens is we're going to be creating a cylindrical shell because it's going to be a very, 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 very small shell that's going to be rotated around here. Okay, so this little line right here is just going to be rotated around, and it's going to have this small little width. And so what happens is we take this, we're going to do that for a lot of them, but we're going to take that right there, and you can see that this shell, we're going to find the volume of that shell. Okay, we have the height of the shell, which we see is the height of our function. So it's going to be f of x, which equals y. We have our x sub 0 value, so whatever we put in there, it's x sub 0, whatever we have right there. We also have a volume, or the width of it, it's going to be very, very skinny. So I'm going to take this, and actually I'm going to cut this in half, or actually cut it like right there. And so when I do that, I'm going to lay that shell flat. And what you see is that we're going to find the volume of this shell by using a little geometry action. And so here's that little tiny shell right there. And what we realize is that this, as we said before, this is going to be f of x sub 0, like that. And now, which is our y value. And now this distance from here to here, well, that appears to be the circumference of our circle. Now, how do you find circumference? Well, that's 2 pi r. Now, r in this case, the radius, is actually from the line of revolution, all right? All right, so the x, our axis of rotation, and our value where we have there. And so that's our r. Now, it just so happens that that r is whatever x sub 0 is. And so we're going to have 2 pi x sub 0 there, okay? And that's going to be the length. Our width right there, or our height, however you want to say it, that's going to say, we're going to say that is going to be some sort of delta x. But we're going to use this notation because that's going to be our differential. And so putting everything together, what we're going to do is we're going to take an infinite amount of these little shells, okay? And we're going to be rotating them around, all right, at all these different positions, okay? And we're going to add them all together. So how do we do that, okay? Okay, is we're going to use what's known as the shell method, and we're going to set this integral. So unlike using cross sections that are going to be circles, what we're going to do is we're actually going to take this right here, and we're going to go from A to B. So here's our A to B. Okay. We're going to take this equation. So to find this volume, it's actually going to be 2 pi x. So whatever x value we have. So x is going to be the radius. all right, of our shell from the axis of rotation, the distance for axis of rotation to any one of these values right there. Okay, and then we're going to multiply by our height, which is f of x. So whatever the distance from that point to that point is going to be. And then we have our depth, which is going to be dx. And that, my friends, is how we do the shell method. That's our little equation. So instead of having pi and then having r squared, we actually have this equation right there. And that is what's known as the shell method. So here's the basic standard form. So we have 2 pi r, all right, just like we have right there, 2 pi r times our radius times the height times dx. Or if we want to put it in terms of y, if we rotate around a horizontal axis, we can have radius, height, and dy right there. And so how can we solve this? Well, we would set this up this way, and we just go and say 2 pi, give it integral from 0 to 1. We would have x, we would have our function x minus x squared and dx, and we put that in our calculator and solve for that volume. And that'll give us our volume. All right, so that's the shell method. I'm going to do some other problems in solving and setting up the shell method when we're going to do this in the next video.